We're constantly hearing about competing scientific ideas. But how do we actually decide which one is stronger? Is it just a gut feeling, or is there a real objective way to know? Well, it turns out the answer boils down to one single, really powerful idea. All right, to get our heads around this, let's start with a little puzzle. Take a look at these two theories. Theory A is pretty simple, right? All planets in our solar system orbit the sun. Can't argue with that. But then look at theory B. It gets a little more specific. All planets in our solar system orbit the sun in perfect ellipses. Now, they both sound kind of true, but that one little extra detail, that's where everything changes. So here's the big question. Which of these two is actually the better scientific theory? And, the real kicker is why. It's not as obvious as it looks, and the answer hinges on this absolutely brilliant idea that helps us sort the really solid science from the claims that just, well, don't hold up. And that big idea is falsifiability. It's a concept that comes from the philosopher Karl Popper. And honestly, it's like the secret key to unlocking this whole puzzle. It really all comes down to one thing: how much risk a theory is willing to take when it makes a claim about the world. So what on earth is falsifiability? Well, to put it simply, for any idea to even be considered scientific, there has to be some way, at least in theory, to prove it wrong. Think about it. If a theory can explain absolutely anything and can't possibly be proven false, is it really telling us anything useful? It's kind of like a boxer who never gets in the ring. A real scientific theory has to be willing to step up and potentially clash with reality. Okay, and that brings us to this next term: potential falsifiers. I know, it sounds a bit academic, but it's a really simple idea. It's just the list of all the possible observations that would totally contradict a theory, that would prove it's wrong. And here's the cool part. The longer that list is, the bolder the theory actually is. So let's apply this to our puzzle. Let's look at theory A, orbits the sun. There's really only one way to falsify that, right? You'd have to find a planet in our solar system that just doesn't orbit the sun. That's it. But now, look at theory B, the one about ellipses. Oh, this one has way more ways to fail. It's wrong if a planet doesn't orbit the sun, sure, but it's also wrong if a planet orbits in a perfect circle, or if it has some kind of weird, wobbly, non-elliptical path. You see? Theory B's list of potential failures is way, way longer. Okay, so it's pretty clear that one list of potential falsifiers is longer than the other. Now, in science and logic, there's actually a formal name for this kind of relationship. It's called the subclass relation, and it gives us a really solid objective way to compare these things. And the logic here is super straightforward. The theory with the bigger list of ways to be wrong is the stronger theory. It's kind of like this. Imagine theory A's single potential falsifier is in a small box. Well, that small box fits perfectly inside the much bigger box that holds all of theory B's potential falsifiers, with plenty of room to spare. Because B's list literally contains A's list plus a bunch of other stuff, we know for a fact that theory B is making the much bolder claim. You could actually break this down into 3 super simple steps. Step 1, you just lay out the list of potential falsifiers for both theories. Step 2, you check if one list is what we call a proper subclass of the other. Basically, does one list fit entirely inside the other one? And finally, step 3, the theory with the bigger list, the one that contains the other, wins. It has a higher degree of falsifiability. See? It's a really clean, logical process. Okay, but why? Why is having more ways to be proven wrong a good thing? This seems totally backwards, right? But this, right here, is the big aha moment. Because being bolder, being more falsifiable, comes with some amazing payoffs. First up, there's something called empirical content, which is just a way of saying how much a theory tells us about the actual world. A theory that says no to more possibilities, a theory that forbids more things from happening, is actually telling us more. Because theory B rules out circles and wobbly paths, it's giving us a much sharper, more informative picture of reality. It has high empirical content. Theory A, by being more general, just doesn't tell us as much. Second, the severity of the tests. Since theory B is sticking its neck out with more specific claims, we can hit it with much tougher tests. We're not just checking if planets orbit the sun, we're checking exactly how they orbit. It's a much harder exam to pass, and that's precisely what makes it a stronger theory if it actually survives those tests. All right, now for an idea that is seriously counterintuitive: logical probability. You would think the better theory is the more probable one, right? Nope, it's the other way around. The better theory, theory B, is actually the less probable one. And why is that? because it's making a much more specific, much riskier bet. Think about it. The chances of a planet just orbiting the sun in any old way are pretty high, but the chances of it orbiting in a perfect ellipse, that's way lower. Science loves the long shot because when a risky, improbable theory turns out to be right, the payoff in knowledge is huge. So this is really the bottom line. In science, being risky is a good thing. A theory that puts itself out there, that's super specific, that practically begs to be tested and proven wrong, that's what we consider a strong theory. It's the exact opposite of being vague and hiding from a challenge. Now, to really make this idea click, there's a fantastic metaphor that nails it perfectly. Let's think about a scientific theory as if it were a net. This just sums it all up so well. A vague, weak theory is like a fishing net with giant holes in it. Sure, it's not going to get snagged on anything, but it's not going to catch any fish either. But a strong, bold, specific theory, that's a net with a very fine mesh. It runs a much higher risk of clashing with experience, of getting snagged on the racks of reality, but that's also why it's able to catch the really small, important details about how the universe actually works. And this whole idea can be summed up perfectly in this table. It just lays out the logic we've been talking about. Look at that top row. If the list of potential falsifiers for one theory fits entirely inside the list for another, then the theory with the bigger list, the one that contains more ways to be wrong, is just flat out the better theory. It's a really powerful tool for thinking critically and seeing which scientific ideas are truly the strongest. So we're left with this really amazing thought. A scientific theory's greatest strength is actually its vulnerability. The very best ideas are the ones brave enough to be easily proven wrong. And that makes you wonder, right? When you look at all the cutting-edge science happening today, which ideas are the brave ones? Which ones are taking the biggest risks, inviting the toughest challenges, and trying to cast the finest net to capture a little more reality?